Hello everyone, and welcome to our fourth online lecture in which we will cover the basics for doing proofs. So this is the outline of the lecture. So we'll talk about what counterexamples are, and then we'll define basic properties and definitions for integers. We'll introduce the basic strategy for doing proofs, and then we'll talk about things such as factors and primes, rational numbers, and finally we'll introduce, if there will be time, proof by cases and the division theorem. So know that in this lecture, especially in part 1, we'll introduce a lot of definitions that you guys have to know to be able to do the proof successfully. So make sure to pay attention during this lecture, revisit it, rewind it, and so on, so that all of this terminology and definitions that we introduce sync in properly. Okay, so let's first talk about cause and effect, which we also call implication. And this is related to the implication operator that you guys already learned about in the context of propositional logic. So in the language of math, we want to move from English words to this if-then template. So as an example, maybe if we use plain English, we would say whenever n is an even integer, then 2 times n cubed plus n is divisible by 3. And if we translate this into a more formal language of math, we should use these keywords if and then to give it structure. So we say if n is an even integer, then 2n cubed plus n is divisible by 3. And so here we have this implication statement where this part of the sentence on the left, n is an even integer, implies the part of sentence on the right, which says that 2n cubed plus n is divisible by 3. Now, of course, these implication statements are not necessarily true. So we can ask ourselves, is the above example true? So how would we go about testing this? Well, one thing we can do is we can try to plug in a couple of even integers and see whether this holds. And if we try doing that, it seems that it holds. But clearly we cannot do this for all integers. So that's where proofs come in. So we would like to prove such sentences for all integers, and not just to test them on a few. Another example that's not necessarily true is, for example, if P is a left-handed person, then P is smart. So clearly this implication does not necessarily hold. So let's now briefly revisit the implication operation and the associated concepts. So if you recall, we denote implication with this arrow symbol. And we read this as if P is true, then Q is true. If we flip the order of Q and P, we read this as if Q is true, then P is true, and this is called a converse. Then we have a contrapositive, which is not Q implies not P. We read it as if Q is not true, then P is not true. So we will use this concept of contrapositive to do proofs that leverage it later on in this class. And finally, we have an inverse, which says if P is not true, then Q is not true. So try to memorize this because we will use them in our proofs. Okay, I already mentioned counterexamples when I talked about that statement connecting even numbers to that expression. And so for the implication P implies Q, a counterexample is when P is true, but Q is not. So that's the only case when the implication is false. And then in searching for counterexamples, like I already mentioned, just because we haven't found one doesn't mean that the implication is indeed true. So for example, if we have an implication that talks about integers, even if we search through, million different integers and we don't find a counterexample, it doesn't mean that the implication holds always. And this is where proofs come into play. Using proofs, we can prove an implication that holds for all possible integers. Okay, a little bit more definition reminders. So we've seen this symbol before, and it means that something is equivalent. So it means that entities on one side can be substituted for the one on the other side. So we've seen this symbol, for example, when we were doing those propositional logic proofs using equivalence rules. Also, this IFFF is short for if and only if, as in P IFFQ. And so that basically means that P implies Q and Q implies P, meaning that both implication and converse are true. And the symbol that is a shorthand for this is this double-sided arrow. Okay, now let's define odd and even integers. So an integer m is even if and only if. So remember, we read this as if and only if there exists an integer n such that m is equal to 2 times n. An integer m is odd if there exists an integer n such that m is equal to 2 times n plus 1. And we will leverage this theorem. We will use it without proof, that every integer is either odd or even. So when doing our own proofs, we will leverage existing well-known theorems, and this is one of them. And we are not going to really go into details of proving them. Okay, another really useful property that will come up in our proofs about integers a lot is so-called closure. So what does closure mean? It means that whenever the operations of multiplication, addition, or subtraction are applied to integers, the result is another integer. So the set of integers is closed under the operations of multiplication, addition, and subtraction. Notice that there is an interesting operation that is missing from this list. I think it's quite obvious that that's division. I think it's quite obvious that division is not closed for integers. And so we'll talk about division separately and define some of its properties. So more properties of integers. If n, m, and p are integers, then n plus m is equal to n plus n. So integers are commutative. And also n plus m times p is equal to n times p plus m times p. So it means that integers are distributive. If n and p are two integers, we say that n is divisible by p if there exists an integer q such that n is equal to p times q. So remember the term divisible. Okay, here are some basic tips for doing proofs, and we'll do a few examples so that this sinks in. But I will still kind of try to state them now, and we'll leverage them afterwards. How do we do proofs? We use the definitions to express things that reveal fundamental properties about objects that we are doing proofs about. For example, about integers. The variables that we use in proofs represent any element in the domain. So that's how we are doing proofs for all integers, for example. then you should not use the same variable to represent two different things. So if two things in your proof are potentially not always equal, then don't use the same variable for them. Then we apply rules and properties, some of which we just introduced in the last couple of slides, that are true for element in the domain. And we combine all this into resulting conclusions that will then also be true for any element in the domain. So we'll see in part 2 on a couple of examples how to apply these proof tips in practice. So the basic there are a lot of different methods for doing proofs. The basic one that we'll start with is called direct proof. So when the implication P implies Q can be proven by showing that if P is true, then Q must also be true. So by using this proof, we show that the combination when P is true and Q is false never occurs. And to do such a proof, we assume that P is true, and then we use rules of inference, the introduced definitions, and previously proven theorems. One example is that all integers are either even or odd, to show that Q must be also true. Indirect proof, on the other hand, is the one where we use an equivalent implication that we can prove, and by doing that, we also prove the original implication if the two implications are equivalent. So we'll see examples of indirect proofs as well. Okay, more terminology. Yeah, don't get scared by a lot of terminology. It will kind of sink in as you start doing the examples and so on. And I also suggest that you go back through this video and kind of revisit the terms that you maybe forgot about. So we say that P element of Z, note that this symbol Z denotes the set of integers, is a factor of n element of Z if and only if, we read this if and only if, there exists m element of Z such that n is equal to P times m. In this case, we also say that P divides n. And we can use the divide symbol to form a predicate. So this bar here, we read it as divides. So P divides n. Of course, every integer has an associated set of factors. And the following predicates are always true. 1 divides n, and n divides n. Now, n, where n is a positive integer, is so-called prime number if the only factors it has are 1 and n. And then we say that m and n are relatively prime if they have no divisors in common. That is, there is no k that divides both of them. Okay, let's switch now from integers to define rational numbers. We'll do proofs about rational numbers as well. So number r is called rational if and only if there exist a and b that are integers, such that r is equal to a divided by b, or a over b. And rational numbers, also called fraction, can be expressed in many equivalent ways. For example, 1 over 2 is equivalent to 2 over 4 is equivalent to 3 over 6. And it is always possible to choose integers. The set of rational numbers is denoted with this symbol Q. And now a number is irrational if it's not rational. Pretty straightforward. And just to remind ourselves a little bit about how rational arithmetic works, take a look here of how we do addition and multiplication. Okay, so here is an example proof It's a simple proof, and it denotes the steps of this direct proof. So what is our proposition we're trying to prove? We want to prove that for any rational number r, the number r plus 1 is also rational. So first, let's state this proposition as an implication. So r element of Q implies that r plus 1 is also element of Q. Now we want to spell out various properties of our hypothesis. So hypothesis is this expression on the left of the implication. So we know that r is rational, and from the definition of the rational number, we know that r is equal to a over b, where a and b are integers. Great. So now we should try to express the conclusion in terms of the hypothesis and its properties. So in the conclusion, we have this expression r plus 1, and we want to prove that that's rational as well. So when we plug in the hypothesis, the property of the hypothesis, we get that a over b plus 1 is equal to a over b plus b over b is equal to a plus b over b is equal to c over b. So we introduce this integer c that is the substitution for a plus b. How do we know that c is also an integer? Well, we know that because integers are closed under addition. And so if a plus b are integers, then if a and b are integers, then a plus b is an integer as well. Okay, and then we just have to state a conclusion. So because r plus 1 is equal to c over b, where c and b are integers, based on the definition of what rationals are, r plus 1 is rational. And that concludes our first proof. It is customary to put QED after you finish proving something to mark the end of your proof. So it's a nice practice to have. Okay, great. We did our first proof. We'll do much more complicated proofs in this class, but this is a nice one to get us started. So another type of proof that we have is so-called proof by cases. So sometimes it's really hard to prove all possibilities at once. So we partition the possibilities that we have for the hypothesis into a finite number of cases, and then we prove each of them separately. So for example, if we have this proposition, if n is an integer, then m, which is equal to n squared plus n, is even. So it might be really, really hard to prove this directly. And so this is a common example we can use proof by cases. And what are the possible cases for n going to be? Well, we know that from our theorem that integers are that every integer is either odd or even. And so those are the two cases that we can leverage to do this proof. And we'll show how this will work later on. How do we know that all integers are either even or odd? We know this by leveraging an existing theorem, like I already mentioned. So sometimes in our proofs, we are going to refer to existing theorems that are well known. And this is one such case. Okay, we already mentioned that division is not closed under integers. And so now we are going to look into different terminology and properties that surround division. So this symbol here, we read it as divided by, and the output of this operation is the quotient that we get. So 5 divided by 2 is 2. 13 divided by 3 is 4. So there is also, when we do division like this, there is also a remainder present. And so we denote a remainder using either mod or this operator, which stands for modulo. And so, for example, 5 modulo 2 is 1, 12 modulo 4 is 0. Things get a little bit trickier with negative numbers, so you have to be careful. Minus 22 modulo 6 is 2, because 6 times minus 4 is minus 24, plus 2 is minus 22. So you have to be careful with negative numbers. Okay, now that we introduced division and modulo, divided by and modulo operations, let's look into the division theorem. So the division theorem states that for all integers a, positive integers b, there exists q and r that are integers such that a is equal to b times q plus r, and r is between 0 and b. So here b is divisor, q is quotient, and r is the remainder. So this is the theorem that we can use in our proofs when we have to prove properties about division. And here q is a divided by b and r is a modulo b. And here we have some examples. So 49 is equal to 10 times 4 plus 9. And here b is 10, q is 4, and r is 9. 25 is equal to 5 times 4 plus 4. And again, we have to be careful with negative numbers. Minus 13 is equal to 5 times minus 3 plus 2. We are looking for this plus here. And r has to be greater than or equal to 0. So the remainder can never be negative. So remember that. The remainder can never be negative. Okay, so that's the division theorem. And finally, I'll end this lecture with showing a few useful subsets of the set of integers z. We have the set of positive integers. We note it with z with this little superscript plus. Similarly, we have the set of negative integers. And finally, we also have 0. And in this class, we consider 0 to be neither positive nor negative. Okay, so with this, I will conclude part 1 of lecture 4. And in part 2, we are going to do a couple of example proofs where we will employ the properties and theorems that we introduced in this lecture. Thank you. Bye.